In this session, I am going to discuss the analysis of statically determinant trusses. This lecture addresses two questions. What is a statically determinant truss and how to analyze it? A truss structure is an interconnected network of slender members, each capable of carrying an axial force only. The force is either compressive or tensile. Theoretically speaking, no shear force or bending moment is present in truss members. Here are a few truss configurations usually seen in roofs and bridges. Howe truss, Warren truss, Pratt truss, K truss. Generally, we assume truss members are connected to each other using frictionless pins. This means if we have two truss members that are joined together, one has the freedom to rotate relative to the other. In other words, truss joints cannot resist any bending moment. Since neither the joints nor the members of a truss are designed to carry any bending moment, applied loads need to be placed at the joints only. No load should be applied directly to the truss member itself. Here is a simple truss structure with 5 members. The frictionless joints of the truss are labeled A, B, C, and D. The truss is subjected to a horizontal force of 5 newtons at joint C. The entire structure rests on a pin and a roller. A truss is said to be statically determinant if its member forces can be calculated solely using the equilibrium equations. Algebraically speaking, if the number of unknown forces equals to the number of equilibrium equations, then the truss is said to be statically determinant. So, how many equilibrium equations can be written for a truss structure? The total number of equilibrium equations equals 2 times the number of joints in the structure. So, if the truss has 4 joints, we can write 8 equilibrium equations for it. Why 2 times the number of joints? I am going to answer this question in a minute. For now, let's just accept it as a fact. But what about the number of unknown forces? The total number of unknown forces in a truss equals to the number of its members plus the number of its support reactions. Here, the truss has 5 members. Each member carries an axial force which needs to be determined. So, there are 5 unknown member forces. Further, since the structure rests on a pin and a roller, there are 3 unknown reactions. The pin provides 2 reactions, and the roller has 1 reaction. Therefore, the total number of unknowns is 5 plus 3, or 8. In this case, since the number of unknowns equals to the number of equations, the truss is said to be statically determinant. How do we analyze such a truss? How do we calculate the axial force in each member? There are several truss analysis techniques. Here, we are going to explain and illustrate a technique called the method of joints. This technique is a direct application of the principle of static equilibrium. According to the principle, if a structure is in equilibrium, then not only the equilibrium equations must be satisfied for the structure as a whole, but they also must be satisfied for any of its parts. For example, if conceptually we cut a beam into 3 segments with the correct internal forces shown at the cut points, then the equilibrium equations must be satisfied for each segment if the entire structure is to remain in equilibrium. We can apply this principle in order to analyze statically determinate trusses. Here is our simple truss. Let's draw the free body diagram of the entire structure. Keep in mind that each truss member carries an axial force only. Let's refer to the axial force in member AC as FAC. Similarly, let's call the force in member BC FBC. We denote the force in each of the remaining members in a similar manner. Now, let's conceptually separate the members from the joints. That is, we divide the entire structure into 9 segments. There are 5 member segments and 4 joint segments. Let's look at the segment containing member AC. We know the member carries an axial force, but we don't know the magnitude of the force. We also don't know if the force is compressive or tensile. Since I want to draw the free body diagram for the segment, I need to assume a direction for the force. I am going to assume the force is tensile. So the free body diagram for the segment looks like this. The only force present in the diagram is the unknown tensile axial force in the member labeled FAC. I am going to draw the free body diagram for the other member segments in a similar manner. Each member is assumed to carry an unknown force. The member is assumed to be in tension. Now, let's draw the free body diagram for the joint segments. Let's examine joint A first. It connects members AC and AD. Since member AC is attached to the joint, the axial force in the member also acts on the joint. We show this by placing FAC on the joint. Note that the direction of FAC at the joint is opposite to the direction of the same force shown on the member. This is the case because the two forces must cancel each other out. That is, if we reconnect member AC to joint A, the sum of the internal forces must vanish. Obviously, this happens only when the two forces are kept in the opposite directions so that they cancel each other out. There is one more member force acting on the joint, the force in member AD. Again, we place this force at joint A in a direction opposite to how the force is acting on member AD. This completes the free body diagram of joint A. At joint B, there are 2 member forces, the force in member BC and the force in member BD. Joint C has 3 member forces acting on it, the force in member AC, the force in member BC, and the force in member CD. At joint D, there are 3 member forces, FAD, FBD, and FCD. Now we have the complete free body diagram for each segment. As I mentioned before, for the entire truss to be in equilibrium, each segment must be in equilibrium. We can easily see that the equilibrium equations are satisfied for each member segment. The 2 force vectors shown in each segment cancel each other. That is, their sum equals 0. And since there is no bending moment or shear force acting on the free body diagram, the moment equilibrium equation is automatically satisfied. So now let's turn our attention to the joint segments. When we say each joint has to be in equilibrium, we are saying at each joint, sum of the forces in the x direction must be 0. Sum of the forces in the y direction must be 0. And sum of the moments about the joint must be 0. Note that the moment equation is automatically satisfied since all the joint forces pass through the joint. So we only need to show that the other two equations are satisfied. Let's see how this works for joint A. Using the geometry of the truss, we can calculate angle alpha. It is 45 degrees. Then we can write sum of the forces in the x direction equals AX plus FAD plus FAC cosine 45 equals 0. And sum of the forces in the y direction equals AY plus FAC sine 45 equals 0. Note that we have 4 unknown forces, but only 2 equations here. It is not possible to find these unknowns yet. Let's number these equations 1 and 2. We need to repeat this formulation for the other joints as well. For joint B, angle gamma can be easily calculated from the truss geometry. The angle is 45 degrees. The two force equilibrium equations for this joint are sum of the forces in the x direction equals negative FBD minus FBC cosine 45 equals 0. Sum of the forces in the y direction equals BY plus FBC sine 45 equals 0. Let's number these equations 3 and 4. For joint C, we have sum of the forces in the x direction equals FBC sine 45 minus FAC sine 45 plus 5 equals 0. And sum of the forces in the y direction equals negative FAC cosine 45 minus FBC cosine 45 minus FCD equals 0. These equations are labeled 5 and 6. Finally, for joint D, we have sum of the forces in the x direction equals FBD minus FAD equals 0. Sum of the forces in the y direction equals FCD equals 0. These equations are numbered 7 and 8. So we have 8 equations and 8 unknowns. We formulated 2 equations per truss joint. That is, the number of equations equals 2 times the number of joints. And since the truss has 5 unknown member forces and 3 unknown support reactions, we get a total of 8 unknowns. Since the number of equations equals to the number of unknowns, we can easily solve for the unknowns. We can either solve the equations simultaneously using a standard technique such as Gaussian elimination method, or we can use shortcuts to speed up the calculations. Let's solve the problem rather quickly without using a standard technique. I am going to scan the joint-free body diagrams looking for 2 types of joints. 1. A joint with only 2 unknown forces. Because if such a joint exists, then the 2 forces can be calculated directly using the joint's equilibrium equations. Or 2. A joint having exactly 1 unknown force in either x or y direction. Found one. Joint D has only 1 unknown force in the y direction. Therefore, using equation 8, I can solve for FCD. FCD equals 0. Now, if I replace FCD in the joint free body diagrams, with 0 we get. Scanning the diagrams again, I notice joint C now has only 2 unknowns. Then I should be able to solve for the unknown using equations 5 and 6. Here they are in the simplified form where FCD is replaced with 0. 0.707 FBC minus 0.707 FAC plus 5 equals 0. And negative 0.707 FBC minus 0.707 FAC equals 0. Solving them for FAC and FBC, we get FAC equals 3.55 newtons. FBC equals negative 3.55 newtons. The free body diagrams are now further simplified. Note that joint B now has only 2 unknown forces, FBD and BY. So I am going to use equations 3 and 4 to find these unknowns. The equations are, solving them for the unknown I get By equals 2.5 newtons. FBD equals 2.5 newtons. If we now examine joint D, we can clearly see that FAD is also equal to 2.5 newtons. The remaining joint, joint A, now looks like this. There are only 2 unknown forces remaining, AX and AY. They can be determined using equations 1 and 2. AX equals negative 5 newtons. AY equals negative 2.5 newtons. The negative sign for some of the calculated values means that the assumed direction for the force is incorrect. More specifically, we assumed AY to be upward. In reality, it is a downward force. We generally present the results of truss analysis by writing the force magnitudes on the members and marking the compression member with a capital C and the tension members with a capital T.